random variable xn. We're going to let those be a random sample of size n that are two things. Number one, we're going to say that each one of these x sub i's, I being any one of these between 1 and 10, we're going to just say that each one of these x sub i's are all independent of one another. And the second thing that we want to clarify is that every one of these x sub i's, so every x sub I is a random variable from the same probability distribution. And these can be discrete, continuous, doesn't really matter, as long as they all come from the same distribution. So as long as we're independent and we all come from the same distribution, these two things combined, these two ideas combined here are usually called IID. So you'll see that written. So these two things are called independent and identically distributed. So that's what you'll see it called. And then another thing that we just pull out here is that for this number 2, same probability distribution, is this thing is generally called the underlying. So you'll hear me probably say the underlying distribution. And which has a mean itself, and I mean itself has a mean, which has a mean. And the way I'm going to differentiate each one of these is to say that this is mean x, this is the mu x, and it has a standard deviation of, and a standard deviation, I got my I in there, standard deviation of sigma x. So I'm just using these little sub x's to differentiate between the the underlying probability distribution and the distribution of the sample mean. So in other words, soon we'll be looking for what is mu of x bar and sigma of x bar. So that's how we'll differentiate between the two. Okay. Here, let me put this IID next to that, because that's in general what you'll see. IID is saying that these two things are happening. All right, so let's go down to our example here, and you'll see that all we're talking about in the example is we're going to roll a 6-sided die. So that's going to be our underlying distribution, and we'll let x be distributed as. So if we have a fair die, you'll see this. People use the die a lot because it's an easy one to, especially a fair die. 3, 4, 5, 6, and then we know we have 1/6. If it's a fair die, we have 1/6 of probability of being in any one of these two, or any one of these 6, the support for this distribution. What does that look like pictorially or picture-wise? Right, this is a pretty simple one to draw. So if I have a 1 through 6, and we have a probability of 1/6 here. It looks a lot like the uniform distribution, where I have a 1/6 probability for each one of these. And we could put a box on there if we wanted to, but I think this is fine. And these are all supposed to have the same exact height. So that's what it looks like. The question is, or some of the questions you might ask, so since this is the underlying, so this will be the underlying distribution for us. What is the expected value of x? I think we can calculate that one pretty quickly. The sum of x, so x times p of x. So go back to your notes for that one. It's just 1 times 1/6, 2 times 1/6. So it's that weighted average. And if you do that, if you multiply that sucker out, you end up getting 3.5. So that's going to be equal to our underlying distribution here. And then the variance of x is equal to, well, if we're going to use the shortcut formula, then we need the expected value of x squared first, which is the sum of x times x squared, p of x. And that'll take a little bit of multiplication to do. But if you did it out, I think you'd get, this would be 15.1667. And then we use the shortcut formula to find the variance. We know that, minus 3.5 squared. I guess we could have substituted this one in as well. So 15.1667 minus 3.5 squared. The variance would end up being 2.91667. So this is sigma x squared. And then if I take the square root of that, so to get sigma x, I take the square root of 2.91667. Square root, it'll take me a second here, 2.91667. What will be 1.70783. Okay, so write these down. We're gonna multiply these out whenever we get into R, because these are important for us to remember as far as what the underlying distribution is. Okay, let's do this. Let's go to R now. So we're going to go to R, and we're going to simulate. So we're going to simulate many die rolls. I'm going to call it, forgive me if I call this dice because I'm used to saying dice, but it's one die that we're talking about. And we're going to simulate many of these die rolls, and then we're going to look and see, well, how close are we to the actual expected value, and how close are we to the actual variance or standard deviation. So that's the idea behind this. That's the next part. And then what we're going to do is so number one is we're going to simulate many die rolls and compare to our x bar for the sample versus the expected value mu x, because we know it should be 3.5, but we're going to find out that it's random and it's not necessarily going to be 3.5. It's going to be some number. And then what we're going to do is we're going to take a bunch of these, right? So not just one of these, but a bunch of them, and then we're going to take this, and then we're going to plot it in a histogram. So I'm going to take a whole bunch of these, and we expect that it'd be somewhere around 3.5, but sometimes you're going to get numbers 2.5, and sometimes you might get numbers over here at 4.5. It just depends on what happens with those, but we'll let n equal 30. So let's say n is equal to 30, and we'll do a bunch of these, and I think many of them will be around this. Now, it's not going to be exactly 3.5, but many of them will be around 3.5, and then you'll have a little bit less down here, and maybe a little less down here, but we want to see the results of the simulation, and that's how we'll see the results, is we'll look at a histogram of the results. not histograms, but just a histogram of the results. And then we'll try to figure out, well, what does this mean about the distribution of the sample mean x bar? So that's really the question that we want to answer. And we'll come back to it. Okay, so we'll start sharing R. All right, I'll delete all of these since I've already been doing some stuff in R here earlier. And we'll let x equal 1 through 6. We'll let p of x equal, I don't know, 1/6. So we're going to recalculate 1/6. 1, 2, 3, 4, 5, and 6. Enter. So mu, I'm not really sure why that keeps coming up. So mu x equals the sum. So this should be 3.5. So it'll be x times, oops, not capital, times px. And we see that we get 3.5. So look over here. And mu x2 is equal to sum of x squared times px. So mu x squared was that 15.166 number that we saw. And then v, so the variance of x equals mu x2 minus mu x. That should be the 2.91 number. And then sigma x equals the square root of, and that's the 1.707. Okay, looks like we are getting all the same, or those same numbers that we talked about earlier that I got. All right, now what we want to do is we want to simulate. So simulate rolling a 6-sided die and show the stats of the rolls. And we're going to start off with 30, and then we'll sort of work our way up. So we'll go roll is equal to, so I'm not sure if you know the R code for this, but if you do a sample, so sample is a function, and what it does is it will, you tell it what the things are that are in your sample, and you're just going to randomly take one from it, right? So in our case, we want to go from 1 to 6, and then we want to tell it how big you want your sample to be, and I want it to be 30. So I think we said that a few minutes ago. We'll let our small n be 30. So what this does is it does 30 dice rolls. So it's picking numbers between 1 and 6 30 times, and I got to tell it that I want to replace. Otherwise, it will just take one number at a time, and then you'll be done after 6. So replace is equal to true. There, make sure that it's all capital letters, and then Control Enter, and then we can print roll. I'll print it this first time, and I'll take that out just to see that there are 30 numbers in there. You can see it over here. So integer between 1 and 30, and here they all are. And we can then just calculate the mean of roll 3.46. Okay, so we were pretty close on that one. If you're doing this at home, you should get something different than mine, unless we had the same seed. And then 1.73, we're pretty close to what our, so if you go back and remember what our sigma x was 1.707, this is 1.7369. We don't expect to get exactly the true value for this. Well, how could we get closer to it, right? So right now I'm at 3.46, which is a pretty good, let's do a, I'm going to take out this print so we don't need to see it every time. I'm going to do another one, and I get 3.63 and a standard deviation 1.75. So we see that every time I do 30 rolls, 3.6. I get something different. And you do it again, 3.16. Yeah, that wasn't great as far if you're looking to get as close to 3.5 as you can. And you see what the standard deviation is. Okay, so we see that the statistics are not coming out exactly like we would expect, right? Remember the word expect. Now that's not what it's going to be if you did 30 rolls. If you did 2 rolls, you wouldn't expect to get 3.5. But how could we go about making this probably closer? It's probably using something different than 30. Maybe I'll use 100. So let's do 100 rolls, and we would expect to get something a little closer. So you can see down here 3.54. That's getting a little closer with the 1.69. Okay, I think we had a pretty good roll that time. What happens if we did 1,000? 0.48. Maybe we didn't have. I guess it's closer. It's closer to 3.54 was 0.04 off. 3.481 is 0.019 off. Right. So we could. So let's go back and let's see if we can get even closer to that. Maybe 10,000 rolls. And we don't want to print these off because it's 10,000 numbers between 1 and 6. But what is my mean? Now we're getting a lot closer, 3.01. I mean, so if you did 100,000, you could see it was a bad 100,000 roll. It looked like. Let's try it again. Or maybe we got a good one last time for the. Oh yeah, you can see it's getting smaller. But again, we don't expect it to come out to exactly 3.5. Probably rarely would it ever do that, but it's getting closer and closer and closer the larger that I put this guy in. Okay, so what I said that we wanted to do next after we did this single one time, let's find out what the mean is. I want to do a whole bunch of those. And then I want to find out what the distribution of all of those X bars are, because this is one X bar that we printed off here, that's 3.497. This is another X bar that's 3.51. This is another X bar, and you could sit here and do this over and over again. But what I'm going to do is I'm going to have R capture what those are, and then we're going to do a histogram of them. All right. So in order to do that, what we want is to create a function, and I'll call it mean die rolls. It's going to equal to some function. Oops. Tell it that I want small n. Small n is going to represent something, and big N is going to represent something else. And we'll see. Let me go ahead and put it in there what those represent. So we'll let n, the small n, be the number of die rolls per X bar. And we'll let capital N be the number. Let's see, the total number of X bars to find. Okay, so all we're going to do is just copy this thing up here, controls. We don't need it yet. Here, let's find a mean rolls. I'm going to set that sucker equal to 0. All that's doing is initializing something that I'm going to capture all of these means in, and then I'm going to go for I n 1 through all the way to n. So the total number of means that I'm going to have will be the capital N, or X bars, if you will. And then I'm going to say mean rolls I, right, the ith one, because all this is doing is going through. It's going to do the first one, and then we want, yeah, we'll come back to that. So we'll let rolls equal to control V. So up here, all I did was I copied this, I pasted it down here, and now I'm going to let one particular instance of a whole bunch of rolls, and I don't want it to be 100,000 every time. I want it to be whatever I passed into my function. And in this case, it was n. So remember what n is, the number of die rolls per X bar. And this is going to be 1 X bar. So I'm going to have that number as my rolls. And then I'm going to say, well, mean rolls sub I is going to be the mean of the rolls that you just did. Is there anything else that we need? I don't think so. Maybe, yeah. Okay, so and we can just return this number. So return. So what this is returning is a whole bunch of X bars. So mean rolls. All right, so take a second and just check this bad boy out and make sure that it makes sense. So this is going to give you a sample of n die rolls, small n, the total number right here, the total number of die rolls per X bar for one X bar. And then this thing's going to come in here, it's going to calculate an X bar and it's going to put it into the ith one. And then it's going to come back in, so let's say I is 1. Then it's going to come back on the second time, it's going to do it again. Same number of die rolls, right? And then it's going to capture a second X bar, and it's going to come back in and do a third one. And it's going to capture a third X bar. So what you're getting is a bunch of X bars out of this thing. And then what we want to do for that is I'm going to call it MR or X bars is equal to mean die rolls and you just run this, control enter, and then we can pass in n, which is we'll let it be 30 for right now. And then the next question is, well, how many of these X bars are we going to capture? I don't know. Well, maybe we'll do 1,000 of them. Then I'm going to do a histogram. I'm going to do a histogram of all of those X bars just to see what they look like. And if you want it, it'll be frequency unless you tell it probability is equal to true. Again, make sure that it's all capital letters when you're true. And then, okay, so let's see what this thing looks like. Control enter. And we get a histogram . All right, so what does that histogram look like? Well, it definitely doesn't look like a histogram of a uniform distribution, right? So the die roll is 16161616, but now this X bar business looks a lot like a normal distribution. So this is, and it's got a little bit of variance in it, right? So we can do another one. Let's just do another one, see what it does. Or just spread out between 2.5 and maybe 4.5. We'll do another one. Maybe we'll do 10,000 of them this time. All right, so we see sometimes you get a really small X bar and sometimes you get a really large X bar. But in general, it sort of goes around, it lies or ends up falling somewhere on the 3.5. So it's getting closer and closer and closer to our actual mean. Well, I mean, most of the time it's on our actual mean, but it's not getting closer yet, right? How could I make this distribution get smaller? In other words, sort of squeeze it in towards the 3.5. The way you do that is you change this number. So I can make this as big as possible, and it's just not going to help us out, right? So if I did the histogram of this, it's still going to be spread throughout the 2.5 to 4.5. But what if we wanted to get it closer and closer and closer to 3.5? I claim that if we did this, if we made this instead of 30, make it 100. Remember that? Well, now you got, so no longer is the 2.5 is the left limit, and 4.5 the right limit. Now it's 4.0. And if you did 1,000 of these, I'm going to go ahead and decrease this number by, I don't want it to take forever. Now we get closer and closer, right? So 10,000. Wow. Yeah, I probably overstepped my bounds, but let's see. And now we're getting really, so it's 3.45. It rarely gets it. So if you're doing 10,000 of these, rarely does it get outside 0.05 away from the actual mean. So the question is, so what's going on with the distribution of X bar? There's something going on there, right? So it's getting closer to the actual mean, and this distribution of X bars is getting smaller and smaller and smaller. So really that's the question that we want to answer right now, is what's happening there. All right, so we're gonna go back and do a little bit of math. So what we saw is that it didn't look at all like this distribution, the distribution of x bar. It looked a lot like a normal distribution, and we saw the bigger we made n, the tighter that distribution got. So let's think about what that looks like. Okay. So first of all, we just need to understand that x. Yeah, let me change this. So the first thing we need to understand is that x bar is a statistic. So is a statistic, and it's random. So what is the statistics? X bar is simply this. It's equal to, so that would be x1 plus x2 plus ... plus xn, all divided by n, where x1, x2 ... xn are IID random variables. Remember what that means. So we talked about that earlier. IID is independent and identically distributed random variables. So like our example up there, each one of those die rolls came from that uniform distribution. Here, what we're saying is they don't have to come from any particular distribution. They just need to be IID, so that they're independent and they're identically distributed. So as long as that's true, then we can calculate what the expected value of x bar is. And that's going to be equal to the expected value of x1 plus x2 plus xn, all divided by n. And it shouldn't surprise you that x bar is random. X bar is random because x1 is random, x2 is random, all of these are random. So it shouldn't surprise you that this x bar here is random. And it has a distribution. So that's what we're trying to figure out. So what is the expected value of that distribution? Well, we're about to figure that out. Okay, so what happens when I might have expected value of this? Well, that means I can take a constant out. So n is constant. We sort of decide on that at the beginning, like we did earlier. It was 30, then it was 1,000, or 100, then 1,000. But we can take that constant out, and we can see that this becomes x1 plus x2 plus xn. And these are capital letters, if you remember. And what that means is that it's 1 over n, expected value of x1 plus the expected value of x2 plus ... plus expected value of xn, right? So of the underlying distribution. So what do we call that, the expected value of the underlying distribution? Remember from above, it's just mu x, and this is mu x, and this is mu x, right? Because they're identically distributed. Remember they're all identically distributed with this underlying distribution, and that mean of that underlying distribution is mu x. So we get how many of these? Well, just like you would expect, there's n of them. So 1 over n times n mu x is equal to, so these cancel, and you're just left with mu x. So what we're finding here is that mu x bar, right, is equal to expected value of x bar is equal to the mean of the underlying distribution. Okay. Now we need to figure out what the variance is, because we saw that something's happening with these x bars. Whenever we had a whole bunch of them, something happened to it. So let's find the variance of this. So all we're doing is basically taking x bar, substituting in what the equation is for x bar. So x2 all the way to xn divided by n. And if you remember from our lesson a couple lessons ago, when we started talking about, well, how do you find the variance of a linear function here? So we know that we can take 1 over n out just like we did above, except when you take it out of the variance, it's squared. So you'd square that, which is 1 over n squared, and then times the variance of each one of these. So it would be the variance of x1, and this is quantity, right? Plus the variance of x2 plus dot 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 plus the variance of xn, which we know that the variance of x1, it has an underlying variance. So that'd be sigma x squared. This one would be sigma x squared, and so on and so forth, so that we had this 1 over n squared times n, because we have n of these, n sigma x squared, which would equal to 1 over n sigma x squared. One of these would cancel off one of those, and you're just left with 1 over n. So it's worth stating. So sigma x squared, x bar squared, is equal to the variance of x bar, which we just calculated, is equal to 1 over n times sigma x squared. So what we're saying is, if as n gets larger here, the variance of x bar gets smaller, which is what we saw in our example. When I let small n in our example get rather large, what happened was the distribution of x bar got really, really close to the actual expected value. So let's go ahead and state the two. Actually, there's one more thing I want to say. So sigma x is equal to sigma x bar is equal to sigma x, the underlying distribution, divided by the square root of n. So if you took the square root of both of this, you would get sigma x over the square root of n. So it's worth stating again that mu x bar is equal to mu x. So the underlying distribution. So this is the sample mean. And this is the underlying distribution. And then sigma x bar is equal to sigma x divided by the square root of n. Okay. All right, so the next thing that we're going to talk about is this central limit theorem. Very important in the world of statistics is that you understand what the central limit theorem is saying. So although it's beyond the scope of this course, the central limit theorem actually answers the question. So although it's beyond the scope of this course, so go take a probability models course, a statistics class, or a high-level statistics class, and you guys will walk through the central limit theorem. It takes it'll take a couple of days to sort of get all of the theory that you need. But what it does is it answers the question. So it will answer the question. So it answers the question on the distribution of x bar. And we'll just state it. So what it says is there's two things that one of two things had to be true. So one, so x1, x2, dot, dot, dot. So this should look familiar. Xn are IID normal random variables. I'm going to say if. So if one, if this is true, or, so one of these two, or x1, x2, xn are IID, and I'm going to put this in red, from any distribution. Pretty important. And n is greater than or equal to 30, then we get the one of the most important results in statistics that helps us do lots and lots of things. We get that the distribution of our sample mean is a normal distribution with mean of what we just showed, with a mean of x, mu x, which is the underlying distribution, and a standard deviation of sigma x over the square root of n. So I'll throw this in purple. This is one of the most important results in statistics, and allows us to compute confidence intervals, to do hypothesis testing, and other things. Okay, that's all I got for this class. We'll see you next time.